This is our AP Stats 9.3 video. We're looking at significance tests again, but this time for a sample mean. So first, make sure you're dealing with a sample mean, not a proportion, before you'd use any of these procedures and calculations. So let's look at an example problem and what we would use this for. So here we've got a student group that claims that first-year students at a university study 2.5 hours per night during the school week, but a skeptic suspects that they study less than that on average. So each of these parts that are in bold and italics are key parts to know about how to put together the problem and what we need. So you know your null hypothesis is the claim that there's no difference. So it'd be that the null hypothesis would be that mu equals 2.5 hours, and what we suspect is that it's actually less, so that would be our alternative hypothesis. So this is the question that we're going to ask. We're going to look at how we do that, and keep in mind that here we know the sample mean and sample standard deviation, but not the actual population standard deviation, so we're going to have to use T procedures. So let's look at the details of how you would solve this problem. And while we're doing this, think about how a confidence interval relates to what we're doing now with the significance test, where we estimated plausible values for a true value in the population with a confidence interval. Now we're testing a claim about the population, so they can both do similar things as far as determining whether something is a value is plausible. So ZAPTAX, remember our little acronym, Z for proportion, T for sample mean. That's because we usually don't know the actual standard deviation for a sample mean, whereas we can calculate it with a proportion. So we have to use a different standardized statistic, so we use T instead of Z. Keep in mind the differences between the conditions for those, because we're dealing with not a proportion, and that a T statistic changes with sample size, so we use degrees of freedom, which is the sample size minus 1. Conditions are the same as before. Now the only thing that's different is we're looking at our null hypothesis here. So we're not looking at it in terms of the test statistics. So pretend like you don't even have your sample taken yet when you're doing the first two parts of the problem. You're just checking your claim based, and everything's based on that claim because we assume it's true. Remember the normal condition? If the population is normal, or we have a sample size greater than or equal to 30, then we're fine. The distribution, the sampling distribution should be approximately normal. If not, we got to look to see if it's roughly symmetrical with no outliers, and then this condition is still met, and we call that being robust, meaning the approximations are still accurate, even though we don't have it as normal as it would be with the sample size over 30. And independent, we got to make sure we don't sample more than 10% of the population. So remember, T is just like Z, our standardized test statistics saying standard deviations from the mean, except for it uses the sample standard deviation. So S sub x represents the standard deviation of our data set, not the actual standard deviation, which we represent with sigma. X bar is the mean of our data set, so that's the actual mean of whatever the sample we got is. And then mu naught is the parameter that we're hypothesizing. So our claim that we're testing would be that. So that's like the mean here, because our curve would be centered around the claim, since we're assuming that that claim is true. So our goal here is to test to see if the data that we get is far enough away from the claim that we can say it's not plausible, that it would happen so infrequently that the claim is not true. And so we can reject the claim and then assume the alternative hypothesis. This is what your calculator does when it runs a significance test. It takes TCDF, it looks at the area under the normal curve, whether it's greater than or equal to the T that it gets, or less than or equal to, depending on what the alternative or whatever you suspect might be the actual case if you can reject the null hypothesis. So that's from our alternative hypothesis. If you go to tests and you go to a t-test for this, then you don't have to worry about doing these steps, which is why I suggest using that. We just make sure you go to draw when you do that, so you get a good idea of what the calculator is doing and what the actual p-value means. So it means how likely we get our sample statistic if the claim is really true. So is the claim plausible? Here's your multiple choice question. So pause now and look at the summary of Chapter 9, Lesson 3. Look back on this outline online, and then answer the multiple choice, and then we're going to finish doing the free response question. I'm going to do half, and your free response will be finishing that question. So pause now and answer why and when do we use t instead of z for most problems involving sample means. A nice picture of what we're talking about when we're looking at a t-test and what it means to reject the null hypothesis or fail to reject it. The claim is here. If the claim is true, then we should get a normal distribution around it if our conditions are met. And if a value is far enough away from this mean in terms of our standard deviation, then we can reject this claim and say it's not plausible. That's what alpha is. So it's saying, what's plausibility? If it would happen by chance 1 in 20 times, is that plausible? So we usually use 0.05 or 0.01, and sometimes we use 0.1 as levels of significance. So could it happen 10%, 5%, or 1% of the time? Here for a two-sided test, this compares a confidence interval to that too. So confidence interval for a two-sided test will correspond to a 90% confidence interval. So a 90% confidence interval, if the sample mean was here in this rejection region, it wouldn't capture, the upper bound wouldn't capture our claim. On the other side of the curve, if it was here, then the lower bound of our confidence interval wouldn't capture the claim. And remember, a value being outside our confidence interval means we're saying it's not plausible. And that's the same thing we're saying here. We're just saying what percent are at that value or more extreme. So confidence interval gives you that extra information. So we have our null hypothesis that we'll always have an equal sign there because it's a claim, and that's what we're centering this normal curve around. And you're always going to want to state what alpha is. Remember, we're using t for a sample mean if we don't know the true standard deviation, and in your do step of your problem, you need to show degrees of freedom when you do that. So if we're doing a two-sided test and you did it by hand or you used TCDF on your calculator, you would have to get the probability that it's less than the sample statistic you got, so wherever it is and to the left, and then multiply that by 2. Since it's a two-sided test, we're looking at either side of the curve. So our p-value then we would have to multiply it by 2. Now, you don't have to worry about that if you use the t-test, because your calculator goes through and does that when you put in your alternative hypothesis. So use the calculator. It helps you with that step. Just understand that that's the difference, and that's if we don't have a suspicion that the true value is greater than or less than, or like we looked at in that fraud problem where they said any percent that's different from 30.1% of records starting with a 1 shows them that it's likely that there's fraud. So it could be way above or way below. So in that case, we use a two-sided test. So think to yourself now, how would this change if it were one-sided, if alpha was 0.05? What would happen? It would just be one side of the curve here. If our alternative was less than, then the p-value would all be on one side, so the whole area would equal 0.1 if our alpha level was 0.1. So this area would be bigger on this side, twice as big, because it didn't include this value. And for that reason, at 0.1 there, that'd be 0.1 on either side, it corresponds to an 80% confidence interval. So try drawing that right now so you can get a sense of what I'm saying. If alpha was 0.1 and it was one-sided. Of data that we'll be using in this chapter is paired data, where you have a difference. For example, if you want to look at like the mean salary of men and women in one country, and you subtract the two, and we look at how far that is from 0. So we're looking to see if there's a statistically significant difference. So in that case, we'll have two sets of data, and we'll have to either subtract the summary statistics, or you might be given a whole list, and you'd have to put them into L1 and L2 separately to run the significance test for that, or just make L1 and L2 and then subtract and have L3 do that for you in the calculator. We'll go over how to do that in class. So that's called comparative studies are often set up that way because it's a more convincing investigation to show a difference in two, like maybe a control group and then the treatment group. So two observations might be there. So you have to measure the same quantitative variable twice. We can call these, look at these differences in each pair. And if conditions are met, we can use T procedures. So we'll go over calculating p-value by hand as well as in the calculator, and I'll give you one way in the video right now. So also keep in mind, statistically significant on these means the p-value is less than whatever alpha is, so that'd be rejecting. So a test is called statistically significant if we have enough evidence to reject the claim. the null hypothesis. So that would be a small p-value, which is strong evidence against the null hypothesis. So confidence intervals sometimes give us more information because they give us a range of values. So how far are we from that? There's a lot of different things we have to look at before conducting these tests, like power of a test. So we want to minimize the probability of type 1 and type 2 error. One other last small note is that the Hawthorne effect is when like an increase in productivity or some other variable occurs just to the fact that people know that there's a study occurring. So knowing that somehow changes the data you'd collect, which would obviously be a type of bias. Okay, here's your free claims that first-year students study 2.5 hours per night during the school week, and a skeptic suspects that they study less. Random sample of 30 first-year students. Sample means 137 minutes, standard deviation is 45. And we're going to look at how we use this information about no outliers. That's going to be used in conditions, and we want to test at the 5% significance level. So first we do the state portion of the problem. State the problem that we're trying to answer, the null hypothesis and alternative, and the significance level, as well as what the variable is. The null hypothesis that mu equals 150, the alternative, we suspect it's less, and we define what it is, that mu is the true mean number of hours students at this university do per night during the school week. Our next step would be to check our conditions and plan. So we had a random sample, so we have an unbiased estimator of the parameter. Our random conditions met. Our normal condition would be 30, so the essential limit theorem states the sampling distribution is approximately normal. The independent condition would be less than 10% of the population, so we can assume that there are at least 10 times 30, 300 students at the university if that's met, which is reasonable. So we can use formulas for standard deviation. To finish the problem, you're going to go ahead and find the degrees of freedom, the t-statistic, using your calculator or using the table, the p-value, and then conclude in context based on our p-value and the significance level, based on what we know about significance tests. So you can do this by going to your calculator and typing in that, and then scroll to the right to tests and go down to t-test. If you have summary statistics, if you're given the mean and standard deviation of your sample, then you're going to use stats, summary statistics. If you're given the data, then first you would have to go to stat edit, put in the data into your list, and then you'd scroll over to data and tell it what list to use. Now, if you put in the summary stats, you'll have to put in the claim from the null hypothesis first, the sample mean and standard deviation for the sample size, and then right above the calculate and draw buttons, you put in the alternative hypothesis. Is it not equal to? Is the suspicion in the alternative hypothesis, or is it less than or greater than what's proposed in the null hypothesis? So choose that, and then go to draw, and get a good sense of what it looks like, where the p-value is in terms of our normal curve, and try calculate as well. Then click on the homework and submit those parts as your free response.